Hello everybody, welcome back to the Gregorius math video. Today we'll be looking at, this afternoon we'll be looking at product spaces and the product topology. Okay, but first we have to look at the Cartesian product. Basically how to multiply, take the product of two topological spaces. The product of 3 and 4 is 12, I think. But what's the product of the real line with itself? Etc, etc. Okay? Today we're going to find out. So first we have to define the Cartesian product. S cross T. So it's written like normal multiplication, but it's pronounced S cross T. And this is what they are talking about when they're talking about, people are talking about when they're talking about the Cartesian product. Okay? S cross T is the set of all ST, okay, such that S is in capital S and T is in capital T. Okay? That's all it is. So, if we immediately jump in with an example, if we have R cross R, well, what does that leave us with? R cross R. This is equal to the set of all, say for example, X, Y. Okay, such that X and Y are in the real line. But what's that? That's just equal to R2. Okay, so look at how we've just constructed R2 by taking the product of R and R. Okay? This is all well and good, and okay, but how, okay, that's all well and good, but how do we put a topology on this? Okay, well, what we do is we form a basis, okay? So given S cross T, where S and T are topological spaces, okay? The basis for the product topology on S cross T, okay, is all of the sets U cross V, for example, where U, a subset of S, is open, and V, a subset of T, is open. So basically it's all of the sets of the products of these open subsets. Okay? So why don't we look at an example? Okay? So if we have a look at an example, we have the cylinder, okay? If we have C, the cylinder, equal to the set of all X, Y, and Z, such that X squared plus Y squared is equal to 1, and Z and 0 is less than or equal to Z is less than or equal to 1. Okay? Now C is actually homeomorphic to the one sphere cross the closed interval between 0 and 1. Okay? Why is this so? Well, R3 is homeomorphic to R2 cross R, okay, via bijective continuous map X, Y, Z, okay, and then just the usual X, Y, Z, okay, like this. Well, now if we restrict these, restricting this map to C, okay, C, a subset, I'll write the C a bit clearer, C, a subset of R3, okay, and S1 cross the closed interval between 0 and 1, a subset of R2 cross R, leaves us with a continuous bijection, which is what we required for C, the cylinder, to be homeomorphic to S1 cross the closed interval between 0 and 1. Okay? Now let's look at a little proposition. Proposition, yeah. Ooh. Okay. Okay. So if we have a little proposition, what do I propose? Well, I propose that a continuous map F, which goes from S cross T to Q, okay, corresponds I think I spelled corresponds correctly, probably not, to two continuous maps, F1, which takes you from S to Q, and F2, which takes you from T to Q. Okay? Now, how do you prove it? Okay? First we'll say that we're given, for example, a continuous map F. Okay, now define F1 to equal F compose P sub 1. I'll define P sub 1 in a second. And F2 equal to F compose P2. Okay, where P1 goes from S cross T to S, and P1 of S T is equal to S, okay, and P2 goes from S cross T to T, and P2 of ST, you guessed it, is equal to T. Okay? Now, the pre-image, we can use the same argument for P2. We're just going to look at P1 for now. The pre-image of U under P1 is equal to the pre-image of U is equal to U cross T. And now if U is open, which is what we're going to assume, U is open to prove that P1 is continuous. U is open, okay? Well, this means that this forms the basis for the topology, and hence P1 is continuous, and F1 is a composition of two continuous functions, hence F1 is continuous. And of course you can use the same reasoning to prove that F2 is continuous. Okay, Now, let's assume that we're given it the other way round. So given two continuous maps, so we're given F. Okay, so if we're given F of Q equal to F1 of Q, comma F2 of Q, okay? These are of course completely different F1 and F2s to the previous part of the proof. If we're given F1 of Q and F2 of Q, okay? Well, by a proposition which I proved in the subspace videos, where I also defined the basis, I believe that's topology 1.3 I'm talking about, okay? I proved that to show that a function is continuous, you can slightly modify the definition and only show that the basic sets in the basis, the pre-images of those are open, okay? So, why don't we let, remember F1 and F2 are continuous, so the pre-image of, say for example, U cross V is equal to the pre-image of U under F1 intersect the pre-image of V under F1. This is open, this is open. The intersection of two open sets is open by the definition of topological space. Hence, F is continuous. Okay, we can do the same thing for F2, but okay, F is continuous. And therefore, we have proven this proposition both ways. Okay, now I'm going to prove one more thing about products and then I'm going to say goodbye. Okay, so the final property I'm going to show is that S cross T is Hausdorff if and only if S is Hausdorff and T is Hausdorff. Okay, so for now I'm going to show just that S cross T is Hausdorff if and only if S is Hausdorff. And you can show for yourself that if S is Hausdorff and T is Hausdorff, then S cross T is Hausdorff. Okay, so I'm just going to show it for S, but again, the same argument can be used. The same argument can be used for T. So, for S to be Hausdorff, okay, so let S and S prime, let S intersect S prime equal the empty set, meaning that they're distinct points, and S prime are in S, okay, and T is in T, okay? Now, this means that the pair of points ST is not equal to the pair of points S prime T, okay? Now, let Q prime and Q, subsets of S cross T, be open subsets of S prime T and ST respectively. Okay? Now, what this means is because Q and Q prime are in the product topology, this means that Q can be written as U cross V, where U is an open subset. So U is open subset of, just remember that U is open, okay? And V is an open subset of T. Okay, just remember that they're open. Okay? So Q can be written as U cross V for some open U in S and some open V in T. Similarly, Q prime can be written as U prime cross V prime for some other U prime subset of S, V prime, subset of V. Sorry, not subset of V, subset of T. Okay? Now we want to show that U intersect U prime is empty. Okay? Which would show that S is Hausdorff, okay? Because these two are open subsets of S, remember. So, let's do it by contradiction. If U intersect U prime does not equal the empty set, that implies that there exists some S double prime in the intersection U intersect U prime, okay? And such that, okay, the pair of points S prime, the pair of points S double prime, T, their pair of points S double prime T are in, well, they're in U, well, what are they in? They're in U, U intersect V, and also they're in U prime intersect V. Okay? Sorry, U prime intersect V, yeah. Okay? Oh, sorry, U prime intersect V prime, yeah. Okay, here we go, yeah. Okay? But now this is where we have fun, because that would imply that U intersect V intersect U prime intersect V prime does not equal the empty set, which can't be true because S and S prime were distinct points, meaning that S is Hausdorff. Okay? And you can use the same argument for T. Now, I'm going to leave it as an exercise to you to show that if S cross T is compact, if and only if S is compact and T is compact. This was a terrific Tuesday for my channel, I believe. 2 videos in one day. At this rate, the Harry Ball theorem is not far. Goodbye.